This is lecture 16.1, part D, measuring gas pressures. All right, in this lecture, we're just going to look at basically two different instruments for measuring gas pressure. And the first one of those is manometers. Manometers come in two different forms, open-ended manometers and closed-ended manometers. We'll look at both of those. Very simple calculations, and then we will take a quick look at gauges, which will also be pretty simple. All right, so this is a manometer, and basically it's just a U-shaped tube here that's full of mercury, and this diagram doesn't have it, but there's a little valve here. And so you can take your gas sample, connect your gas sample to the U-tube and open the little valve, and the tube is full of mercury. And when you open the valve, this column of mercury will move up and down depending on the pressure of the gas in this sample. Okay. There are two kinds of manometers, as we said before in the previous slide. This is an open-end manometer, and what that means is that this end of the tube right here is open, so that it's exposed to the atmosphere. Right, so that's just like an open tube, like the top of a drinking straw or something like that. Okay. The other kind of manometer is a closed-end manometer, and it's the same as the open end in all respects. It has this little valve here. The difference is that the end here is sealed, okay, and this little chamber here, just like in a barometer, this little chamber here above the mercury is a vacuum. Okay, that's the only difference between the open end and the closed end. Okay. Excuse me. So now we'll look at how we can use this manometer to calculate the pressure of the gas in this little container over here. All right, so first I want to point out something in the at least one of the textbooks. I think this is from the open source textbook. You see diagrams like this in a lot of textbooks, though. I find this to be a really irritatingly confusing diagram. It's got a whole bunch of different setups for these manometers, and has three different equations down here. This part is H times rho times G. That's just the pressure of a column of liquid using that hydrostatic pressure equation that we used a couple of lectures ago. And this H times rho times G refers to this column of mercury here, or this column of mercury here, or this column of mercury here. Whatever corresponds to this H, whatever corresponds to that height. Okay. But going back to this, the reason that I think this is a confusing and irritating diagram, and I'm going to show you a way to avoid using this. I don't think you should use this diagram at all. Is it's really kind of difficult to remember when you have to use minus H rho G or when you use plus H rho G. And also in two of these equations, you've got atmospheric pressure, and in one of the equations, you don't. And it seems to me, when I look at this just seems to be like a giant memorization task of which equation goes with which diagram. There's a much easier way to do this that doesn't require any memorization. We're going to see how to look at these manometers and then just figure out what the pressure is without having to worry about any of this memorization. All right, so let's take a look at one of those. Okay, so here's an example of a gas in a, an open-ended manometer in this case. And we want to determine what the pressure of the gas is in this container over here. Okay, this is a typical manometer problem. This is what they look like. in the textbook and on quizzes and exams and things like that. It may be a little bit difficult to see in this drawing, but the column of mercury goes from here to here. So this is all mercury through here. All right. Okay. And we want to calculate the pressure. Okay. Now, as I said before, that previous diagram gives you a whole bunch of equations. You don't have to memorize any of those. All you have to do is look at this, and we'll just apply a tiny bit of logic, and we can work our way through it. Okay. We're going to start by doing the same thing we did with the barometer, and that is just draw a horizontal line through this mercury fluid, right? And we're going to draw the line down here wherever the lower surface is of the mercury, right? There's a surface up here, and there's a surface down here. And regardless of whether it's higher on the left or the right, we're going to always draw that line at the bottom, at the lower level. And just as we did with the barometer, we know that if we draw that horizontal line, then the pressure is constant along that line. Okay. So now we can just look at these two different columns on the left and the right, and we know that the pressure on the left is equal to the pressure on the right. And then we just need to look and see what is pushing down on the left side and what is pushing down on the right side. Okay? On the left side, there are two things that are pushing down, right? There's the gas here, which is exerting a pressure here, pressure of the gas, and there's also this column of mercury, which is exerting pressure because a column of liquid exerts pressure, as we saw in a previous video. So on the left side, we've got the pressure of the gas and the pressure of the column of mercury, and that's equal to the pressure on the right. And on the right, there's no mercury here, right? Because we're looking at this line right here. The only thing pushing down on the right-hand side is atmospheric pressure, because this tube is open to the atmosphere. Okay, so on the right-hand side, we have atmospheric pressure. So this tells us that the pressure of gas plus the pressure of the mercury is equal to the pressure of the atmosphere. If we want to know the pressure of gas, we can do a teeny tiny bit of algebra here and just rearrange this so that it says pressure of the gas is equal to pressure of the atmosphere minus pressure of that mercury column. So what we're doing is we're just subtracting pressure of mercury from both sides. Okay, and so the pressure of the gas is the pressure of the atmosphere, which is here. I should have pointed this out earlier. Manometer questions will usually include some notation about atmospheric pressure in them. Okay, so the atmospheric pressure in this case is 755 torr. Okay, and the pressure of the mercury is this column right here. And I'm not going to write out all of the dimensional analysis, but if there are 10 millimeters in a centimeter, then this height is 357 millimeters. Okay, so that means that the pressure of the mercury column is 357 millimeters of mercury, and of course millimeters of mercury is the same as torr. So the pressure of the mercury column is 357 torr. Okay. So the pressure of the gas is just 755 torr minus 357 torr, which is 398 torr. Beautiful. We didn't have to memorize any equations. We just had to use a little bit of common sense and reason our way through it. All right. Here's another very similar question, again, an open-ended manometer. We've got a gas, U-tube full of mercury. Mercury goes from here to here. We've got atmospheric pressure here, and we want to know the pressure of the gas in this container here. Okay, so we're going to do exactly the same thing we did before. The difference, by the way, the difference here is in the last problem, if you remember, the mercury was higher on the left side, and in this one it's higher on the right side. That was one of the differences in that confusing diagram that I showed you. My point here is that you don't need to memorize all those different equations. It doesn't matter whether the mercury is higher on the left or the right. You could even write the whole, draw the whole picture the other way around. You could do a mirror image of the picture. Wouldn't change anything. Okay. So what we're going to do, just like last time, draw a horizontal line at the lower mercury surface. Okay. And at that lower line, the pressure is constant, right? So that means pressure on the left is equal to the pressure on the right. Pressure on the left is equal to the pressure on the right, okay? And this time, if we look at the left side, there's only one thing on the left, and that's the pressure of the gas, right? And on the right-hand side, there are two things. There's the pressure of this column of mercury pushing down here. And there is also the pressure of the atmosphere, because again, this is an open-ended manometer, and that part right there is exposed to the atmosphere. All right, so the pressure of the gas is just going to be pressure of that mercury column plus the atmospheric pressure. Okay. The difference we've got here is the height of the mercury column was given to us in inches, and you'll see this kind of thing a lot. This can be in inches or centimeters or millimeters, you know, whatever. So you need to be prepared to do that conversion. Okay, let's go ahead and do that up here. Save a little space here. We've got 7.2 inches, and we recall, I hope, that 1 inch is equal to 2.54 centimeters, and that 1 centimeter is 10 millimeters. So we'll check our units to make sure they cancel out. They do, that's great. And if we put that whole thing into our calculator, we get 183 millimeters. Okay. And since that is the height of the column of mercury over here, on this side right here, right, 183 millimeters, this is the pressure in millimeters of mercury, or 183 torr. Okay. So the pressure of the gas then is just the pressure of that mercury column, 183 torr, plus the pressure of the atmosphere, which is given to us here in the problem. And if we add those two things together, we get 931 torr. All right. Easy peasy. Okay. All right. So now let's look at closed-end manometers. Okay. So here's a similar problem with a closed-end manometer, and we'll see the way we approach this is exactly the same. The only difference is that Now the end of the manometer here is closed, so instead of atmospheric pressure getting into the top of that column, this part up here is just a vacuum. Okay? And that's actually going to make these a little bit simpler. Right? If we want to know what the pressure of the gas is, we'll do exactly the same thing we did before. Draw a horizontal line, even with the lower mercury level. And that line represents constant pressure. So we know that the pressure on the left is equal to the pressure on the right. And if we look at what's pushing down on both sides, on the left side, the pressure of the gas is pushing down on the surface of the mercury. So we've got pressure of the gas. And on the right-hand side, we've got this column of mercury. So we've got the pressure of the mercury. Okay? And because there's a vacuum up here, right, there's nothing else pushing down on the right-hand side. All we have is that column of mercury. A vacuum has a pressure of 0. So the pressure of the gas is just the pressure of the column of mercury. There's really almost no calculation to do. Right? So we just need this height of that mercury column. We need to convert that into millimeters. And again, if there are 10 millimeters in a centimeter, then this height, 12.6 centimeters, is 126 millimeters. So that means that the pressure of the gas is 126 millimeters of mercury, or 126 torr. Okay. All right, notice a couple of things. One is that in this problem, atmospheric pressure was given to you down here. Okay, and sometimes it'll say it right in the problem. Atmospheric pressure is 757 torr. Okay, that is a red herring. It's a little bit devious. It's a little bit mean, but you will see that in textbooks, because one of the things in textbooks, and frankly one of the things that I'll be testing, is to make sure that you understand the difference between an open-end manometer and a closed-end manometer. So usually we'll give you atmospheric pressure in both cases, and you need to know that when it's a closed-end manometer, you can just ignore that value. You don't need to include it in your calculation. All right. The other thing is, this problem asked us to give the pressure in atmospheres, so this gives us a chance to practice our conversions from the previous section and to remind ourselves if we're converting between torr and atmospheres. There are 760 torr in 1 atmosphere. Units cancel out, and we get 0.1657 atmospheres. And since we had 3 significant figures in our original data, we should round that. So the pressure of the gas in that little vessel is 0.166 atmospheres. All right, now let's take a look at gauge pressure. Here are a couple of examples of gauges that you might see in your daily life. Anytime you've got a gas cylinder, like in a acetylene tank, if you're a welder or something like that, I'll have a regulator on the top with a bunch of gauges here. This is the gauge on an air pump at a gas station where you can fill up your tires, and this reads the pressure here in PSI. Okay. This is an old school tire pressure gauge. I don't know if anyone's used these. I haven't seeing them around as much anymore, but you stick that little part on the nozzle of your tire, and then there's this little stick that goes inside here, and when you put it on your tire, the stick pops out, and the distance that it pops out of the little cylinder gives you the pressure of the tire. Okay? And here's another example. This is a pressure gauge that you can buy to stick into a football or a basketball or a soccer ball or something like that to measure the pressure, to make sure your ball is at regulation pressure. And you can see this one has a fixed on it. It's got a little needle that you can stick right into the sports ball. Now, all of these gauges have something in common with the way they work and the way you read them. If you go to the gas station and it says inflate your tires to 35 psi, then you just want to go to the gas station, hook up the little pressure nozzle, and keep going until this reading says 35. If the manual says you need to inflate your soccer ball to 13 psi, you just want to pump it up until this thing right here is giving you a reading of 13 psi. Okay. So the pressure that it gives you in the instructions, just basically go with that to match the gauge. Okay. But if you look under the surface, there's something a little bit more complicated and a little bit more interesting going on, and we need to look at that for just a minute. Okay, so here's a typical pressure gauge. This is from a gas cylinder in the lab, and I'm not sure if you might not be able to read it where you are, but it's got the units. It's got two different sets of units. On the inside here, it has pressure in psi, and on the outside, it has it in it's like kilopascals. Okay, and usually gauges, for some reason, they usually have two different sets of units on them. So that's not very uncommon. That's pretty typical. But if you take this gauge here and unscrew it and look at all the guts in the back part of the gauge, what you'll see is something that looks like this. And this part right here is a hollow tube. It's made of brass or copper or something like that. And this hollow tube is connected down here to the gas supply. And what happens is when you open the valve and connect the gauge to the gas, some of the gas fills up this tube. And if there's a lot of pressure in the gas, this tube, it's kind of got a curved shape to it. If you put a lot of pressure in that tube, then it makes the tube straighten out a little bit and it loses some of its curve. If you've got even more pressure, then it straightens. I'm exaggerating here because you can't go outside the thing, but the tube basically straightens out slightly, and that moves the tip of this tube here. And as the tip of the tube moves, you can see there's all these little connecting things here, and then this part here leads to the needle on the front face. Okay. So it works by having the gas pressure inflate this little tube, and that causes the tube to bend a little bit. But there is one more thing that's happening here that's kind of important, is that while the gas pressure is inflating the inside of the tube, atmospheric pressure is pushing on the outside of the tube, because this gauge here is not sealed. So you've got atmospheric pressure in the back of this little gauge mechanism. So the pressure inside the tube is pushing the tube and trying to make it straighten out a little bit, moving this mechanism. But the atmospheric pressure is squeezing the tube and keeping it in kind of the same shape that it was in originally. So what you see on this dial is not just the pressure inside the tube, but you see the result of some kind of a competition between the pressure inside the tube and the pressure outside the tube. So ultimately, what this means is that the gauge is actually reading the difference between the absolute pressure of the gas and some reference pressure. And usually, for almost all gauges, that reference pressure is atmospheric pressure. Okay. So we could also write that this way. Gauge pressure, that's what we read on the dial is the absolute pressure, that's the actual pressure of the gas, minus the atmospheric pressure, because again, the gauge is actually giving you the difference between these two. All right, so let's look at a simple example. This is a gas cylinder with gas in it. We're using blue molecules for the gas, and the little red molecules out there represent the air molecules. And so if we're interested in seeing how gauge pressure works, here we can recall that equation, right? Gauge pressure is the absolute pressure of the gas minus the atmospheric pressure. The gauge is going to give us the difference between those two. So if the atmospheric pressure is 1 atmosphere, and if you're working a gauge pressure problem like this and it doesn't say anything about the atmospheric pressure, just go ahead and assume that it's 1 atmosphere. That's a really good assumption under any reasonable conditions. If the pressure is different than 1 atmosphere, then it's really up to the instructor to let you know that. And if the instructor doesn't say anything, then 1 atmosphere is a good assumption. All right, so atmospheric pressure is 1 atmosphere, and the pressure of the gas in the cylinder is 10 atmospheres. So the gauge up at the top, right, what is the gauge going to read? The gauge is going to read the difference between those two, or 9 atmospheres. That's how gauge pressure works. All right, so here's a simple gauge pressure problem. Let's say we go into the gas station to inflate the tires, and the gauge at the gas station is reading 32 psi. It's not showing any units on here, but those are psi. We want to know, just because we're curious, what's the absolute pressure inside the tire. So we remember our equation here, which tells us that gauge pressure is giving us the difference between the absolute pressure, the pressure in the tire, and atmospheric pressure. If that's the case, we can do just a little tiny bit of algebra, rearranging to solve for the absolute pressure in the tire. And if we do that, in order to do that, we just add atmospheric pressure to both sides, and that gives us absolute pressure is the gauge pressure plus the atmospheric pressure. And atmospheric pressure, I told you a bit ago, you can always assume, oops, oh, that's horrible. You can assume 1 atmosphere. Okay. So the absolute pressure inside the tire is the gauge pressure, which is 32 psi, plus atmospheric pressure, which is 1 atmosphere. We can't add those two things together. We have to do a little unit conversion, and I hope you remember from previous lecture that 1 atmosphere is 14.7 psi. So that means that the absolute pressure in the tire is 46.7 psi, and since since our gauge here that we're reading goes out to the ones place, we should round this to the ones place. 47 psi. That's the absolute pressure inside the tire. All right, so to summarize, there were really 2 things we looked at. We looked at manometers, both open-ended and closed-ended manometers. And for a manometer, it doesn't really matter whether it's drawn this way or this way. The key for these manometers, whether it's open-ended or closed-ended, the key is always just to look at the column of mercury, draw a horizontal line at that lower level, and remember that the pressure at that point, pressure on the left side is equal to the pressure on the right side. If you can do that and you remember the difference between an open-ended and closed-ended manometer, right? Remember that an open-ended is open to the atmosphere, a closed-ended is sealed at the top, so that you have a vacuum. If you remember those two things and you can reason your way through that, you don't have to learn any new equations for using for using manometers, right? And then we also looked at gauges, and the important thing here was to remember that the pressure indicated on the gauge is actually the difference between the absolute pressure and the atmospheric pressure. Okay. I'll say one more note about gauge pressure. If you get a problem that says something about a gauge and then specifically asks you for absolute pressure, that's a question that has to do with gauge pressure, and it wants you to use this equation. But if you've got a question that says a cylinder is hooked up to a gauge and the gas in the cylinder has a volume of 23 liters and a pressure of 17 psi, that's not a gauge pressure question. Just because the word gauge is somewhere in the problem doesn't mean that you need to do this. Usually when a problem gives you the pressure of a gas, it's directly giving you the absolute pressure, so you don't need to worry about this gauge pressure equation. Only do this calculation if the problem is specifically asking you for absolute pressure, the difference between absolute pressure and gauge pressure. If it specifically makes that distinction, use this equation. Otherwise, assume that the pressure in the problem is the absolute pressure. Okay, nice set of stuff we worked through. I feel good about that. You should all be ready to tackle everything in the pressure section of the study guide and in the textbooks. Great. And next we'll start looking at the simple gas laws.